Welcome back to the second session of this chemical kinetic series. In first part, I have discussed the salient features of this very important Lindemann theory, of course, for the unimolecular reaction. In the second part, it is part 2. Now I will derive the more refined theory of unimolecular reactions, and that is Hinshelwood theory. As I have pointed out in my first lecture, that there are some problems in the Lindemann theory, although it was published in 1922, and there is no concept of energy distribution among the different vibrational modes. So therefore, this theory is very important. As I have already told you that this theory, Hinshelwood theory, is comprises of two concepts. One is collision, there is no problem, and you know the concept of the Z, number of total binary collision occurs per unit area, per unit volume. But in addition to that, he used the statistical mechanics, particularly Maxwell-Boltzmann distribution of statistics. And he has not changed the original mechanism, that is, he has not changed the original mechanism. That means here is also a energization process, there is no change. And then product. So there is no change. Only thing is that he used how after that collision, when a molecule acquires some energy, now how that energy is transformed and it is distributed, because each molecules have a capacity to store the translational energy, vibrational energy, rotational energy, but he has given emphasis on vibrational degrees of freedom. I will discuss all these things. And you all know that it's a very simple concept of the collision theory, that if this kinetic energy or that energy, threshold energy, kinetic energy exceeds that threshold energy, then of course the reaction occurs. And that energy is shared among different degrees of freedom. You know that degrees of freedom may be very high. So how that energy is distributed? Unfortunately, I am having that original research paper of Sir C. and Hinshelwood, who is a Nobel laureate. He published this paper in 1927. And if you read, I will request all the students, please go through this very beautiful research paper. And he has mentioned, if I write this, Professor, while deriving this equation, he discussed with Lindemann, because ultimately he slightly elaborated, or I can say modified the Lindemann theory. So Professor Lindemann suggested to me, that means Professor Hinshelwood, that there might be enough collisions for unimolecular reaction if the total energy could be made up by any distribution among a considerable number of degrees of freedom. and he just considers it just like a harmonic oscillator with vibrational frequencies like that, Boltzmann constant. So his theory is based on, suppose there is a change in energy, like first is E, total energy, then E plus delta E, then E1 plus delta E2, like that. There is a large number of degrees of freedom. So this is the original paper I am taking from that internet, and this is the photographs I have also taken from the Wikipedia. Now, as I have already told you, that without the Lindman theory, we cannot derive other theory. So again, I am writing the same equation, same equation is here, and the concept of this K1 and K inverse 1. So therefore, it is a probability, energization and de-energization process. So therefore, I have generally written this equation. But the question is that if I want to here, if I want to know the distribution, I need a formula, and for that I need quantum state, partition function like that. And so I have to calculate this statistical weight factor, the degeneracy. And suppose I am taking the degrees of freedom is S divided by Q, or partition function, particular energy E divided by K. Here is, please bear in mind, here K is the Boltzmann constant, it is probability. So in Lindman there is no question of this probability distribution and nothing, only collision. But here I am just using two terms. So I must know the value of G, I must know the value of this Q also. And you know that there is certain derivation, but because we are dealing with only Lindman theory and then Hinshelwood theory, so I will directly write, I will not derive that how we can get the values of Q, partition function for a harmonic oscillator like KBT, H, omega. Omega is the vibrational frequency and S is the degrees of freedom. So I have to substitute these values of Q, and then I can also write the values of G. It's not at all difficult, but there is some system is there like that. Factorial. I will not derive the values of G. When you will study the statistical mechanics, you will get the why, from where I get all these things, number of states and other things. So, friends, students, you can directly write these values of G and S in order to know the probability, how energy is distributed. And then, of course, we will solve this equation sum. So, the rate constant, you already know that it is, again, this, for collision theory, there is no problem. Now, according to the statistical mechanics, of course, Maxwell-Boltzmann distribution, the probability that a molecule has the energy between E to D. So, I can write E1 plus D delta E1, delta E2. So, that is probability, you know that I can write like that, E minus E by KBT, then delta E1, delta E2, like that, delta E3, divided by, of course, KBTS, like that. So I can write like that. I have here written here. So how I calculate this maximum probability? That is my target. So I have already written to you, that is F is equal to this GS, then QS, partition function. You can write K is not rate constant here, it is Boltzmann constant, please bear in mind. It is Boltzmann constant. Boltzmann constant. So you know that it is just like a statistics. That suppose J quanta, S is number of Box, how it is distributed. And this probability is directly proportional to that number of systems and other things. And you can also calculate, you know these things, because we are talking about this quanta. So E is equal to H omega like that, N is equal to H omega like that. So you need not to be worried about the complete derivation. You just write directly the value of degeneracy here and the values of partition function. Of course, vibrational degrees of freedom and vibration. And then substitute this value in our main equation. Substitute this value in our main equation. So let us see what happens. So you see, I have written this thing. So because you know that the values of G is E, right? Exponential E by KBT H omega S divided by, so H nu KBT S. So this part is cancelled. So what I am getting, E S minus 1 exponential S1 factorial and KBT S. This is I am getting. Now, what I have to do? Now, I have to integrate it, because this is the normal energy of activation. But in order to do chemical reaction, one critical energy is required. So I have to integrate it from, I can write E star also, to infinite. Now it is up to you. If you referred any book, if you referred Ledler, chemical kinetics, so don't get confused. In sometimes in place of capital E, I can write epsilon, and that critical state star or zero you can also. So it is up to you. But here I am just using capital E and E star. You follow my point? Or in order to do the integration, because it is one type of summation. So now I will integrate it. I will just explain it if you don't understand this thing. So this is our case. So let me, what I am doing, I will do the integration like that. So you know that here I have written here EA, I can written here also E star. There is no problem. And of course a very little bit mathematics is here. So it is better I will explain it. And then finally we will get a gamma function. And from that gamma function, I can derive the final equation. So I think don't get excited. I will just solve it, because we will get a very big value. But because you know that there are many types of things, but as because the EA value is greater than KBT, so the integral is well approximated. So we will take a small value. Those who are interested in very high mathematics, they can refer the chemical kinetics. Chapter number 3, there is a reference appendix and the whole derivation is given there. Okay. So just let me explain very simple way so that a student can understand. So I think the derivation part is where. I can do the derivation. Okay. So see it very carefully. So F, what I am getting, first is that E S1, then here S factorial KT divided by just where is that? Just again I am just coming to first point. No, इसमें फिर से आ जाइए इसमें. First point or main equation. What I am getting? ATS actually I am getting. Yes. Now see it very carefully. Here is actually KT. I can write like that. If I just want to write KT S1 multiplied by KT, I can write exponential rules. Very simple. So it is there. So I just, so what I can write like that? I can write E energy, activation energy. Yes. Factorial. Now in place of KTS, what I can write? KT multiplied by KT. It is always Boltzmann constant. No? Boltzmann constant. Don't get confused. Exponential E KBT and delta E. Now I have to integrate it from E star to infinite, or even you can write EA. That is the critical point. So before I do some integration, I have to do some approximation. That first point is that it is a constant. So if I write E star infinite to 1 S and a factorial outside this thing. Now suppose E by KBT is equal to X. Just I am doing integration, very simple integration. E divided by KBT is equal to X, or I can write like that. E is equal to x kBt. Okay, Boltzmann constant. So I can write dE is equal to dx kBt. So I can write like that. So in place of E, you see here very carefully, in place of E, because E divided by kBt is equal to x, so E is equal to kBtx. So in place of this, I can write kBtx. Clear? Then exponential minus E by kBt is equal to x. So it is x. And d, we can write dx kBt. And here is also kBt. So kBt. This kBt cancel. So what I can do? What I can do? Just from this side. So 1 s 1 factorial s, because now we are doing the integration and we give some substitution that x is equal to E by kBt and E is equal to, in one side infinite and another E by kBt. So therefore what I have to write here, of course infinite no problem, but here I can write E star or whatever it is, oblique kBt. So here you see, of course in that side also kBt s inverse 1 is there, right? So what I can write? I can write kBt s inverse 1, right? X s inverse 1 divided by, so that integration becomes very small. S inverse 1 exponential minus x dx. So this kBt cancel. So what I am getting, a very simple formula. Very simple formula. 1 s minus 1 factorial from E star to kBt to infinite. So very simple, x s inverse 1 exponential minus x dx. So there is a, it is again for mathematics students, there is a gamma constant, gamma function. If I integrate it, I'll get the incomplete gamma function s E by kBt s inverse 1 factorial. And this gamma function, if I write like that, so it will get like that, integral is equal to, a little bit mathematics is there, exponential E by kBt, of course E star by kBt, 1 plus E star by kBt plus E star kBt whole square 2 factorial like that. Dot 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 dot. We can write like that E star kBt in place of square. You can write f inverse 1 s minus 1 factorial. As know that as we just go on, I said, but there is an approximation because whenever we solve this thing, we are taking only the vibrational degrees of freedom and we consider only one step, and the values of kb is energy is higher than kBt. So other part can be removed. So if you don't understand things, so you can directly write these things that what you can do, you can directly write these things 1 s1 factorial, you see here like that, you can write that. Then E, now I have just converted E star, right, kBt, just see very carefully, s minus 1 factorial, then exponential, that is E star, now it is star, is critical, divided by kBt. So I am getting this final equation. So if you don't understand these things, so you can directly write these things. In some of the books, if you see Ladler, they have not derived, they have not done the integration, but it is the integration part is available in the appendix part of the chapter 3. But you can directly write this equation. And again, it is approximation because we are considering only the vibrational degrees of freedom, and that is 1, and other part can be removed. Now the last part, what is the limitation of this theory and other things. So there are 3 parts. One part in normal collision theory, and again I can write this our unimolecular theory, which is important, K infinite is equal to, color is not good, yeah, K1, K inverse 1 and K2. I am just deriving this K1. 1 plus K2. This is actually Lindman theory. And another is that Z, K is equal to Z E by RT. It or like that. So now the difference between the collision theory and here, and you know that collision frequency Z or collision rate is directly proportional to the T half. So what I can write that K1, see it very carefully, is proportional to T half multiplied by the probability. This part is the probability. So 1 by T S, and third part is the fraction of molecules, energy distribution among the degrees of freedom. So I can write like that, exponential minus E star divided by kBt, last part. And again I am saying, those who are referring the Ladler or any other book, in wherever I have written the E star, or you can use epsilon also, epsilon 0 star also, just in order to make the difference between normal activation energy and that particular. So if I See it very carefully. Last step. If I take the logarithm, so yellow color, natural log of k1 is equal to, because if I take log, suppose x log of a, right? So half natural log of t, then plus s minus 1, natural log of 1 by t, then minus e, oh sorry, e star I can subscript, no problem. Here you write abt. Is it clear? Now differentiation with respect to temperature. Differentiation with respect to temperature. So I can write in a white color d by dt of natural log of k1 is equal, you know that d by half d by dx log x, d by dx log x, 1 by x. So I can write that 1 divided by 2t. Now you know that d by dx 1 by x t is equal to minus 1 by t. So minus s minus 1 divided by t. Now you know this is a very simple integration, that means this E star, K is a constant, so it is T inverse 1. So nx n minus 1, so minus T. So minus minus, this is plus, so E star KBT square. So now if I take the LCM, so, and you know that, just you remember your BSc classes, that d by dt of log temperature dependence of the rate constant is nothing but the Arrhenius equation. Temperature dependence of the rate constant. That means I can write E. Of course, E by RT square. But here actually I am talking in terms of molecule. And you know that K is equal to R by N. So this is like that. So I am talking about the in terms of molecule. So therefore KBT square. Okay. If I take the LCM, so it is KBT square. If I solve it, so like that, it was just school level things. KBT divided by 2 or half KBT. There is minus, just T, so S minus 1 KBT. And here is simply this KBT cancel, it is E star, like that. So KBT. So what I can write? White color. A little bit mathematics is there. I'm sorry, but you have to solve it. This KB cancel. So I can write E is equal to, you can put half KBT minus, you see here, KBTS, here is minus, plus KBT plus E star. So it is half KB, half kb and 1 plus half, so 3 by 2. So E is equal to 3 by 2 kBt, Boltzmann constant therefore, minus kBt and S plus E star. Again, very simple mathematics, not at all difficult. So E is equal to, you can take common, kb is Boltzmann constant, kBt, so 3 by 2 minus S degrees of freedom plus, so there is a clear-cut distinction between this E and this E. So this is the final equation. So in order to get the exact value of E star, I can write in red color or this color, because that is our E minus kBt, or you can write like that, 3 by 2 minus S. So of course that you have seen the clear-cut difference between these two energies, which is responsible for chemical reaction. Or finally, if I just rearrange this equation, it is again different types of books are given different types of things, and so if I write here plus, so you can call it S minus 3 by 2, just reverse it, and kBt. So by that method, by using the different values of S, maybe 10, maybe 12, maybe 13, and different values of energy of activation, you can calculate the unimolecular rate constant, and which is definitely, there is a good correlation between the theoretical value, but there are certain problems. Now I will come to that point. And one thing is here that in order to distribution of the energy, that is always greater than this. You see, always greater than this. So by that way, that Lindman, there are some demerits. Hinshelwood solved that problem. So the last part is the if I see the K infinite, which is K1 and K inverse 1, is the probability, and then K2. And this side I have also written Z E by R, K2, or whatever it is. So what is the difference between these two things? Difference thing is that means in collision theory and Hinshelwood theory, only one additional thing is there, is factorial 1. This part is there, and then E star or whatever by kBt S minus 1, like that. And then this part is also Z part is also there. So what is the difference? You see that this additional part is there. So when I solve this equation using that Hinshelwood theory, so what I am getting, that this K1 and K inverse 1. So I can write like that, K2, and here is same thing, 1 S minus 1 factorial exponential. Now it is star after this thing, S minus 1 exponential E star by KT. Or no, after the integration we have there. So there is a very good relationship between the collision theory and statistics theory. From collision theory, this part is there, and with the help of the statistical mechanics, we can derive these things like that. Now there is some coming to the limitation, the last part of that theory. So as you have again show you this our final equation that you see, I have already written these things, but those who are not aware of mathematics, they can avoid all these things. They can directly write the final equation as I have already told you. Now this part for 2 factorial, then 3 factorial. So it is better not to use it in sometimes this S is equal to actually n by 2, half n by 2. Somewhere you will see that. And write like that. So better we use this terminology. You see here. Maybe 2, 3, 4 like that. So yes, whatever it is. And ultimately we are getting this final equation. You see, I have already shown you. And here I have written A, but it is actually E star. The difference between, and ultimately we get this final equation. So again, the limitation is, what is the limitation? That first limitation is that vibrational degrees of freedom, the values of S. Because when they perform large number of experiments, it was observed in order to get true experimental value, they have to change the values of S. Just like they have to reduce the values of S. So the theory does not explain why the number of degrees of freedom needed to match the experimental data is only about half of the total number of vibrational modes. Suppose there is K experimental and one is K theoretical, and I am using S is equal to 12. But when I perform the experiment, I have to reduce the values of 12 into 6. So that is not match, there is a mismatch. Second, does not match experimental rate constant accurately. Experimental data often shows deviation at different temperature and different pressure. And for large values of A, there is a strong temperature dependence of the pre-exponential factor. Those who are interested to see some of the values, some of the data, they can say large number of research papers. Some values are also available. The theoretical value and the experimental value. You can check it. But it is a classroom level lecture, so I am avoiding all this data. And third is that you do agree with me that here I am using the collision theory as well as the statistical mechanics. But I have not discussed about any quantum mechanics like that. So when we derive the further equation, then of course, yes. When we do some further explanation, and another very great problem of that fall off, when we plot a graph between 1 by k inverse 1 and 1 by a, as well as simple k1 and a, this is a hyperbola type of thing. So at higher pressure, there is a constant value, but like that. From that, we can also calculate the k infinite, and that at this is k infinite divided by 2. We can also calculate, but why this fall off predicted by the Hinshelwood theory? So a significant improvement, there is no doubt about it, and you have also realized this thing, the difference between Lindemann theory and Hinshelwood theory. But again, this deviation, because when we plot a graph between Again 1 by K1 and 1 by A. It must be there. But again, why such type of things is observed? Has not been proper. I am not saying that he has not addressed all those points. He has addressed, but he is not perfectly. And no explanation for the quantum effect. And does not consider the quantized energy level. This becomes important at molecular scale. So what should we do? I have already discussed the Lindemann theory as well as the Hinshelwood theory. So that thing is that problem, thanks to great scientists, regarding the concept of quantum mechanics as well as the statistical mechanics, can be solved, solved by three great scientists. One is O.K. Rice, second is the Ramsperger. They have given the derivation on the basis of the statistical mechanics as well as the quantum mechanics. And Kallol particularly used the quantum mechanics, quantum mechanical calculation. So I have already prepared a lecture for that RRK theory, but what you can do, that the gist of the RRK theory is that you have to apply the Hinshelwood theory, final equation of the Hinshelwood theory, and then the theory of and the determination of the K2, because ultimate objective is that K1 and K inverse 1 from Hinshelwood theory and it is also K2, and that is E star. I will not discuss today. S and K activity. So thank you very much. And of course that development is 1927. So I have already prepared. Those who are interested in RRK theory, they can refer my work. So thank you very much for patient hearing. Thank you.